I will begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for this class, and just ask that you'd guide our steps, help me to understand what I'm trying to prove, and to be able to not get stuck today, Lord. In your name I pray, Lord Jesus. Amen. All right, here we go. So we are in the midst of working on the proof of the Cayley Hamilton Theorem, and it's not a small theorem. It's an easy enough result to remember, Hamilton Theorem, but we'll get there. So where we are at the moment is this theorem, which is my 4.4.4, which says the following. Let T be an element of the linear transformations on V, where V is finite dimensional. All right. Over F with invariant subspace invariant subspace W. All right. Then the result is this. The characteristic polynomial of T sub W, right, divides the characteristic polynomial of T. So, first order of business, let me just make sure we know what these words mean. Characteristic polynomial of T. So we could maybe use P sub T for that. Like P sub T, I'm going to use X for a change, and that would be the determinant of T minus X, right? And then P sub TW would be the determinant of T sub W minus X. All right. Now, this T sub W, remember, so invariant subspace W, that tells us what? That tells us that T of W is a subset of W, and so therefore we can define T sub W, a mapping from W back to W again, right? Where T sub W of X is just equal to T of X for all X and W, right? I'm sorry, I thought everyone was here, and obviously you were not here. Like, my bad. But the good news is I haven't done anything. All I did was write out theorem 4.444, why is it 2 points? Anyway, 444, and I'm blathering on about what a characteristic polynomial is and why it is that we can talk about the characteristic polynomial of this T sub W, which is essentially T restricted to W. It's a little bit more than that, though, because we're also chopping off the codomain, so it's not V anymore, it's W. All right, so that's that. Now let's look at the proof. And so the proof for something like this, basically, oh man, fine. Proof, suppose the dimension of W is equal to K, and beta sub W equal to V1 through Vk is basis for W, all right? Extend beta sub W to beta V1 Vk plus 1, Vn for V. We'll assume the dimension of V is what? N, all right? Well, notice since W, well, since T of W is a subset of W, right? That implies that T of beta sub W is a subset of, well, did I say beta sub W? That ain't true. That's garbage. That's just not the case. It doesn't have to be mapped to the same set, you doofus. Who wrote these notes? Let's try this again. Let me erase this. My goodness, what is wrong with me? Golly. I would have to have a span of beta W there, right? Span. So here's the issue, though. If we look at the matrix of T with respect to the beta basis, right? We almost did this same calculation last class. It's pretty much the same thing again. So you got like T of V1, beta, beta, right? And so forth and so on until we get to the kth one. And then stuff. I don't care past that point. All right. The thing is, T of T of Vi is an element of the span of beta k, beta w. What's wrong with me? Beta w, many things. For I equals to 1, 2, k, right? Because since T of W is a subset of W, right? By T invariance, we feed the first k basis elements. They're going back to a linear combination of those first k basis elements, right? And so what that means is that this looks like a whatever, 0. And this, how big is that A? Well, I mean, this is just manifestly equal to the matrix of T sub W with respect to the beta sub W matrix as well. Do you see why that is? Because what is T of V1? It's nothing more than T sub W of V1, right? They're the same mapping, they're just different domain, right? So like this is T sub W of V1 all the way out to T sub W of VK. So in fact, if we just look at the top k rows, it's exactly the matrix of T sub W with respect to the beta sub W basis, all right? And once you have that, the theorem becomes pretty obvious because the P sub TW of X we can calculate from the determinant of TW sub beta W, my horrible notation, minus X times the K by K identity, right? And we can calculate P sub T of X as the determinant of A minus, oh my, let me use A, it's easier. A minus X IK up here. There's a B, there's a 0, there's a C minus X times, how big is that one? Well, N minus K, right? So what I'm doing is I'm using the beta coordinate system to calculate the determinant of that transformation. Remember, I can do that because we defined, as we worked out, right, the determinant is invariant up to a similarity transformation, right? So I can calculate the determinant using any choice of basis I like So here I'm just calculating the characteristic polynomial in terms of, the beta basis. But this is nothing more than the determinant of a minus xik, right, times the determinant of c minus x times n I sub n minus k, right? And this is straight up p sub tw of x, right? Because that is a, right? What have I done? You look unduly happy about this board work. No. I'm always nervous if I see a student who looks too happy. It makes me wonder, what have I done? But I should be meaner or something. I don't know. But does this? So what does this show? It shows you that the characteristic polynomial of t sub w divides the characteristic polynomial of t. It's a factor, right? So that's what we mean. All right. So we got that. Yep.
So just over here for the t being beta and then on the inside, is it just supposed to be 1? For the t?
Did I do something funny? T sub which one? Where?
For the t v1, is it just 1 beta in that part?
Oh, thank you. Yes.
Also over here.
That's the matrix, so there's two of them there.
Yeah.
Okay.
This one, is that first? Is it supposed to be for just t sub w on the first row? I don't know if I'm describing that well.
Over here,
Yeah, like the top one.
the top one.
I don't know how to say that.
Ah.
Because we said the Cayley polynomial.
Well, if we can't say it in words, I don't know what other choices we have.
I know, it's terrible. I can point.
Oh, numbers.
Yeah, wait.
We can think in numbers.
The top one?
The top one, yeah.
T sub w or just t?
Oh, that's t sub w. I'm talking about the characteristic polynomial of the t sub w. So I'm just looking at the matrix of t sub w, like that.
So that's equal to the term divided?
Yeah, because the determinant of a block diagonal matrix, well, not block diagonal, upper like this. If it's like this, I can determinant of this times determinant of that's an identity for determinants. So this is literally that matrix. So the determinant of this piece is literally that piece, and whatever this is, it is. I don't care, but yeah. This theorem, we're going to use it for the Cayley Hamilton theorem, but like this has broader applicability for this course than just this particular story arc. Like, so the next theorem, 4.45. Again, we have t as before. Let t be linear transformation on a finite dimensional vector space, and we'll let w equal to the cyclic subspace generated by x, where the dimension of w is equal to k. All right. Then number A, the set x, t of x, t squared of x, all the way on down to t k minus 1. There's a typo in my notes right here. I'm missing the of x on this last one. All right. Is a basis for w. And B, if a naught x plus a1 t of x plus dot 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 plus a k minus 1 tk minus 1 of x plus t sub k, not t sub k, t upper k, tk k-fold compositions of t acting on x is equal to 0, then the characteristic polynomial of t sub w is given by pw of t equal to -1 to the k, parentheses a sub naught plus a1t plus dot 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 a k minus 1 to the tk minus 1, finally plus t to the power k, close parenthesis. Some of this we already did last time, in a sense. Like, let me set up the theorem. Remember, we defined, how, you guys remember how we defined the of x bit here? What did that mean? Thing of x. What does that mean? What's that notation mean here? I guess I'll remind you. So this means x, t of x, t of x, so t squared of x, t cubed of x, and so forth and so on, right? And I didn't quite do it right. What else is there? There's something missing here, isn't there? But I forget. Important. Span. Yeah, span. So this is the cyclic subspace, or if you could say the t-cyclic subspace generated by x under t. And I argued last time that that's an invariant subspace. But if we're talking about a finite dimensional vector space, this is a subspace of V, right? And if this is if the dimension of V is equal to n, right? Then that means that W equal to this thing, it has to has dimension of W, equals to k, which has to be less than or equal to n, right? So that's my first comment. Is like the first sentence of this theorem is already justified by our discussions last class, okay? Is that clear? So then, how do we prove part A? How do we prove that that's a basis? All right, so let's try to look at that. So let's let beta equal to, now I got to be careful here. I'm trying to follow the book. So let's let beta, oh, I think I forgot something that's important. Yeah, I forgot something. What do we know about x here? X not equal to 0 is actually like really critical for x not equal to 0. Because if x were 0, that's definitely not a linearly independent set. It's just a set containing 0, So we're definitely out of luck. But so, all right. So here's the argument. Notice the set just containing x is linearly independent since x is not equal to 0. Okay? And then here's the construction. Let J be largest positive integer for which beta x, t of x, t squared of x, da da da, t of j minus 1 is linearly independent. Now, you guys tell me, why does such a j have to exist?
Because it's a finite dimensional subspace.
Exactly, because it's a finite dimensional subspace, and beta is clearly a subset of W, which is finite dimensional, right? So, all right. Notice then, we can argue that t sub j, right, of x is an element of the span of beta. Why is that? Do you guys understand that? It's a little bit slippery. Sometimes I don't understand that when I'm reading this proof. Can we explain that? Why is that? Notice that t sub j of x is equal to t sub j minus 1 of t of x, right? Maybe I should look at it the other way around. Yeah? No, by construction, tj minus 1 of x is an element of beta, right? Oh, maybe I don't see this. I don't know. So this is definitely a this is still a, oh, rats. I mean, this is still an element of W, obviously, right? Because it's T. This is always where I get stuck. I don't know what to do, guys. I'm sorry. I told myself earlier to just, project confidence here and just slip past it. You guys wouldn't notice. But I foolishly tried to show you, and here we are now. So on page 314 of the textbook, if you're wondering, Inzel, Spence, and Friedberg, right? Yeah, he claims that T sub j, he calls this thing Z, by the way. But anyway, I'm just gonna leave that there. I'm not gonna dwell on it. We've spent enough time already. So there's a small gap here, all right. But hopefully that'll be the last one for today. So why? Now he gives a reason. He says by theorem 1.7 on page 40 of the textbook, all right? And that theorem is the one that's about like spans and vectors inside or outside the span or something. So it may be something relatively simple here. I'm just too dense to see it at the moment. But oh, maybe it's just like clear contradiction, right? Oh, yeah. It's the maximality of the linear independence. That's it. Look. If this is not in the span, right? Think about this. If this is not in the span of beta, then what? Then we can tack that on here, and it's still linearly independent. Because remember, if you take something outside of the span and you union it with a generating set that's linearly independent, you get a new linearly independent set. That's one of the ways we can enlarge a linearly independent set is by simply adjoining vectors outside of the span of the set. But then that contradicts the maximality of this set, being it the largest linearly independent set. And for that reason, this has to be in the span, because if it was outside, it contradicts the maximality. That's it. That's the argument. Oh, I feel so much better. I actually learned something today. Yay. Now, of course, I have learned that in the past, and I have found a way to forget it until the next time I taught it, so there you go. Maybe I'll remember from now on. Let's be optimistic. Now, if that's the case, then what does that mean? Then there exist, if it's in the span, if this is in the span of those vectors, then of course we can do what? We can write, T sorry, I've lost track of, he introduces a W all of a sudden. I don't know, I've lost track of what he called W. Let W be, oh, okay, fine. Let W be an element of Z, right? And then W is equal to like C0 x plus C1 T of x plus dot dot dot, right? C j minus 1 Tj minus 1 of x. All right, great. So in particular, T of W is equal to what? Well, it's equal to, look at this, right? C0 T of x plus C1 T squared of x plus dot 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 plus Cj minus 1 Tj of x. And what does this show? Oh, this shows the thing we've already showed yesterday, which is that this is an invariant subspace, right? So this is in Z, and Z, and Z. This is in the span of beta, which is in Z again, so this altogether is in Z. So this is the book's argument that the T invariance of the cyclic subspace. The thing I didn't do last time was to argue that there has to be a basis for that of this form, okay? That is what's new in the current discussion, is that not only is it invariant subspace, but that the basis for the cyclic subspace generated by X can be written in this way. All right? Okay, so let's look at part B then. So for part B here, yep.
How large are these cyclic subspaces normally? Because it seems like you're going to get a whole lot.
Well, it depends on the nature of the linear transformation, as we'll see. But they could be as big as the whole space, but they can't be bigger than that. It's not a very helpful answer, but it's true. Okay, so like for part B, we use beta, x, t of x, t squared of x, and so forth, right? Tk minus 1 of x basis for the cyclic subspace generated by x, x being non-zero, of course. And note, there exist scalars, a0, a1, dot, 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 a sub k minus 1, such that. So here we go, a sub 0 times x plus a sub 1 times t of x plus dot, 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 a sub k minus 1 t to the k minus 1 acting on x plus t sub k, not sub, I keep saying sub k, but I mean upper k of x equals to 0. Now why can I say that? Why do there exist such constants? Remember, we know that we'd argued previously that this, right, is in the span of beta, right? So we can write this thing as a linear combination of these vectors. Okay? And I'm just rewriting that fact in a way which is convenient for us here. Okay? Partly just to tie into part B. Okay? Now we have satisfied the assumption of part B, if this, all right? So here we go, if this. That's a reasonable assumption based on the data we have here. Now, we should calculate the characteristic polynomial of t restricted to w. Can we do that? So I basically just need to look at what is t restricted to w, you know, with respect to this beta basis, right? So let me just kind of like scribble over here and then put my results over there if you guys don't mind. So the first thing in the basis is x, right? So t of x sub beta, that's actually the second thing in the basis, right? First thing, second thing. So this is E2. Okay, because it's the second thing in the basis. T squared of x, well, that's third thing in the basis. So what we get, you see, is 0, 1, 0, 0, 1, like that. Okay? And this goes on until we get a 1 in the last spot, right? Okay? So here I'm talking about the first k minus 1 columns, right? And then what goes, you know, this is supposed to be plus dot dot dots. Use your imagination. My dashes became ones. It's not helpful. So what goes in how about the last one? The last one's kind of interesting. What is, let's see here. What is t of the kth basis element? What's t of tk minus 1 of x, right? That tells us the kth column, right? Sorry, my board works a little bit unorganized. What I'm doing is this stuff is informing what I'm putting up here, okay? But this is tk of x, right? So this is in fact equal to solving this minus a0 x minus a1 t of x minus dot 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 minus a sub k minus 1 tk minus 1 of x, right? The coordinate of that. Coordinate of that is literally minus a1, minus a0 rather up here, minus a1, minus a2, and down the line, finally, minus a k minus 1. And what's the characteristic polynomial then? So then if we calculate the determinant of, you know, t, we're calculating the determinant of, so here's my pw of t. We've got, what we got is minus t on down the line, minus t. Down here, minus a sub k minus 1 minus t, I think. And then mostly zeros otherwise, but we've got ones on the subdiagonal, I suppose. And then the, minus a sub k. I don't write the next one. What am I doing? Dot, 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 dot. Finally up here, minus a0, minus a1. And it's clear that this is equal to that. Maybe. Let me, in the interest of making it make sense for you guys, go something like more concrete. So suppose we have, example 1. Example 1, we have like, 0, 1, 0, 0, 0, 1, and let's say minus a, minus b, minus c, all right? And then I'm doing minus t, 0, minus a, 1, minus t, minus b, 0, 1, minus c, minus t, right? Because I'm supposed to calculate the determinant of this matrix minus t times the identity matrix, right? I think I'm forgetting there's like some determinant trick here I'm supposed to use, and I don't quite remember off the top of my head, guys. Like, there's a shortcut here I'm not remembering. Or I should have made this homework if I was smarter. Let's see here. So, I guess we can just, goodness. Fine, I mean, I'll do what minus t times what? This guy, right? So minus t times minus c minus t plus b. And then over here, minus a times 1, which is, goodness gracious, minus ct squared man, I have messed something up here, guys. You know what? Maybe it's just not obvious, and like this is just a somewhat difficult homework problem that I'm forgetting. Let's just say that for now, but it is true. Well, I did fill in the other gap, so I'm still allowed one gap, right? Although this may be a sizable gap. I will look at this afterwards and see if I can fix it, guys. I'm sorry. I'm not seeing my way through this at the moment. let us move on before I bury the lead here. So, here we go. Cayley Hamilton Theorem. Let t from v to v be linear on dimension of v equals to n, right? With characteristic polynomial p of t, then p of big T is equal to 0. All right. All right. Note to self, must make that homework problem for next year. Okay. I can't get stuck if it's your homework, right? If it's already your homework and I've forgotten about it, that would be very sad, right? But anyway, here's the proof. If x is equal to 0, then pt acting on x is equal to 0, since p of t is a linear transformation on v, right? We know a polynomial in a linear transformation is again a linear transformation because the composite of linear maps is linear and the sum of linear maps is linear and the scalar multiple of linear maps is linear, and that's all a polynomial in t is. Suppose x is not equal to 0. Right? And let w equal to the cyclic subspace generated by x with the dimension of w equals to k. All right? Then there exists a 0 through a sub k minus 1 in the field for which a sub 0 times x plus a sub 1 times t of x plus dot 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 plus a sub k minus 1 t k minus 1 of x plus tk of x is equal to 0, right? By the theorem that I just almost proved. This part we proved. This part, up to now, we earned this much. And here's the part where it gets a little sketch in terms of what I did today. Moreover, the characteristic polynomial of p sub w of t, right? It's equal to minus 1 to the power k times a sub 0 plus a sub 1t plus dot 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 a sub k minus 1 t to the k minus 1 plus t to the power k, close parenthesis. All right. Consequently, thus, if we do p sub w of t acting on x, what do we got? We've got minus 1 to the k times a0 plus a1 of t dot 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 plus a sub k minus 1 to the big T to the k minus 1 plus to the big T to the power k, all of that acting on x, right? But that is literally equal to minus 1 to the k times Pac-Man, which is equal to 0. Now what's the Pac-Man? Can you see Pac-Man? Should I call it Ghost? It's right here, right? Eh? Uh-oh, I've caused happiness again. I don't know what happened. All right, so this is equal to 0, and that is what we get from feeding x into this, right? So that's 0. So then what? I mean, all I know at the moment is that p of t acting on x is equal to 0, but I'm trying to learn something about, I'm trying to show p of t equals to 0, right? This x is totally arbitrary, except that it's non-zero, right? We already know 0 works. So if we can show that when we feed x into p of t, it's 0, we're done. We've shown that this is the 0 transformation, and that's the Cayley Hamilton theorem. But what did we do at the start of today? Remember what we had at the start? We had at the start p of t, we can write as p sub w of t times some other thing, right? Let me call it g of t, right? In other words, the characteristic polynomial of t sub w is a factor of p of t by the first thing we did today, right? And so when I take p of t and I let x act on it, first of all, these commute, right? So I could have written this g of t and then p sub w of t acting on x. But, oh, that is 0, which means this is 0, which means that p of t is equal to 0. And that's the Cayley Hamilton theorem. That if you plug in the linear transformation into the characteristic polynomial, you get back the trivial transformation. Do you guys have any questions? Maybe I show you an example of the characteristic of Cayley Hamilton, yeah? That'd probably be good for us. By the way, the things that we're doing today, and this is like, tell you what, I'll give you guys 5 bonus points if you can give me a proof of this. Not this necessarily, but the claim, there might be an error in here, all right? But if you can prove that the characteristic polynomial of this matrix is this, then that's worth 5 bonus points, okay? What am I saying? 10 bonus points. It's at least a 10 bonus point problem. I got stuck on it in class, so 10 bonus points. What's that? Oh, okay. All right. Because that gap can be filled. I'm just tired. So, sorry about that. So, an example, if we have t of, let's say, x comma y equal to cosine theta, sine theta, minus sine theta, cosine theta times xy, right? In this case, okay, fine. So then the characteristic polynomial here, so like cosine theta minus t minus sine theta, cosine theta minus t, right? So here's my p sub t of t. We've got what? We got t. I'll write the t first. So it's t minus cosine theta squared plus sine squared theta, right? So if we put this equal to 0, that would be what we would want to do to try to find like the eigenvalues, right? Eigenvalues are zeros of the characteristic polynomial. Phooey. Well, let's finish this thing here. So this tells me that t minus cosine theta squared is minus sine squared theta. So what's that give us? That gives us t minus cosine theta is plus or minus I sine theta, which gives me what? T is cosine theta plus or minus I sine theta, which you might recognize as e to the plus or minus I theta. So your eigenvalues here are complex. Right? This is in fact an example of a linear transformation on R2 which has no eigenvalues, right? If we look at T as a mapping from R2 to R2, no real eigenvalues. Do you guys agree?
Isn't that De Moivre's theorem?
It's a part of De Moivre's theorem, yeah, sure. You probably said it right. That's not a correction, that's just my habit. But look, this is easier if let's put theta equal to pi over 2, okay? Just to make things a little bit easier to see. Then, what happens then? P sub t of t is what? This just becomes t squared plus 1, right? I don't really want to try to plug the transformation in to the one with the cosine and sine because it's too messy. So, all right. Now, so if P of t is supposedly t squared plus 1, that means the identity matrix, right? The identity mapping. So one of the corollaries to this should be that the matrix of t squared plus the identity matrix is equal to the zero matrix, right? That's a little bit easier to check. Like the matrix, the standard matrix of T here with my theta equals pi over 2 choice is what? It's like 0, minus 1, 1, 0, right? What's that matrix if we square it? I think I get minus 1, 0, 0, minus 1, right? And so you can see what happens. The matrix of t squared plus the identity matrix is what? It's minus I plus I, which is 0, right? This happening is the Cayley Hamilton theorem. Alternatively, you could work out the rule for the composition of the map with itself plus the identity map, right? And you could see that, in fact, that's the zero transformation. But anyway, sorry, I was trying to give an easy example at the end of class. I'm not sure I succeeded. Anyway, I should just end this day. I don't even know why I'm trying to teach another class at this point.